Hi, and thank you for joining us for this webinar session on mastering the next generation of Maryland science standards. My name's Francis Vigent. I'm a CEO here at NOADM, and I'm also a former teacher. I started as a high school math teacher, and I spent a better part of 8 years as an elementary and a middle school STEM specialist. So I have a great appreciation for the work that we all do in the classroom to really meet the needs of the standards, but even more than that, meet the needs of the children that are in our care. And thinking about the next generation science standards transition in Maryland, it's important to think about why, kind of connecting our purpose as teachers with why these next generation science standards even exist. And really what it comes down to is not, turning every student into a scientist or an engineer. If that's what children want to become, wonderful. But the bottom line is that it's a focus on critical thinking skills, specifically creative, evaluative, and analytical thinking skills that help students in whatever college or career choice that they choose to make. And if that should be in the sciences, wonderful. But there's another level of that as well, that participating as citizens in society, more and more we are impacted by technology, public investments in technology, or even permissions and permitting and the sorts of industry and things that we have to decide about in our communities. All of these things are more and more technology related and science related, and the ability to think critically and scientifically about those decisions are really great for society in general. So there's a really kind of deep purpose, high-level purpose to all of this in a sense. But when you think about the actual K-12 classroom, for students to be able to develop those skills, the content areas of science, technology, engineering, and math are really the best environment for teaching those skills, because they can be done hands-on, problem-based, active learning, all the buzzwords that kind of fly around this. But the key of it under these next generation science standards is that students really need to be put in the role of scientist and engineer. They really need to understand the relationship between the two and between all these disciplines, and they need to be developing skills which they can then generalize and apply in many different environments. We're going to take a look at that in a moment. So thinking about this, that's where this transition to next generation professional development, new next generation curriculum and materials and all of that comes into play. So to tell you just a little bit about NOADM and kind of who we are and how we take an interest as well in next generation science standards, is that as a group of educators, our focus is really on meeting the needs of children, and we're very excited about the opportunity to teach higher order thinking skills in the classroom under these new standards. We're based north of Boston in Salem, Massachusetts, and we have been helping schools and districts to implement a lot of what has become known as the next generation science standards for the last 10 years. And when you think about what's involved, kind of at the end of materials and curriculum, professional development, those sort of things, they really have to fit together hand in glove. And so that's how we help schools and districts at that level. We don't deal directly with teachers, but what we do is we help the schools and districts actually deliver against these transitions. So that's where we kind of fit in this, and we do it nationally, where we fit in this dialogue. So thinking about this next hour, what I'd like to do is take about an hour to think about what makes these next generation science standards tougher specifically, and again thinking all of this really from the classroom level as educators, because regardless of whether you're an administrator or a parent or an educator, frankly what really matters at the end of the day is how these standards come to life in the classroom and how that produces learning outcomes, it really transforms thinking. So thinking about what makes these standards a little tougher, how these standards link to Common Core ELA and math, and really how the new standards are going to affect, if they haven't already affected it already in your community, the pedagogical methods for science instruction in K-12. And finally, some of the connections between these standards, not only with Common Core, but with art as well, and the arts in general, in terms of how these practices and thinking skills cross over, and the synergies there. So if you're on the live session, I'll let you know. Feel free to drop questions into the question panel. There will be a question panel on your screen. You can drop them in any time, and I will do my best to answer at least 2 or 3 at the end. Quite a bit of content here, but we will do our best to catch it. So without further ado, let's move along here. So there's a great survey that was done in the fall by the Maryland State Department of Education, and it bears taking a quick look at here, because I think it depending on where you're at and where your community is at, I think you're going to find that there's a big lift with these new standards across the state, and the reality is it's across the entire country, and that has to do with really what the standards are aiming at, these higher order thinking skills, but also really their performance-based standards. So this survey looked at about 3,000 educators and some supervisors as well, and asked a bunch of questions. I pulled out about a half dozen here just to point out to you. One of the questions was, do your students have experiences with content aligned to the NGSS in a laboratory environment as part of their regular science class? And it's about 50-50. Now, one of the kind of misconceptions about these new standards, because they are performance-based, is that every student needs access to kind of the black tabletop science lab, and that's a misconception. What a student needs access to is the opportunity to engage in planning and carrying out labs. Now, a lab is really just a planned investigation. That can happen in a cafeteria, that can happen in a gymnasium, it can happen in your average kindergarten classroom with no sink, no closet, nothing, but some basic materials. So, if you don't have a lab, don't feel at a loss. Many people don't have access to a lab. Kind of adding on to that, do your students have experiences with content aligned to the NGSS in addition to their regular science class? So this is really looking at the fact that most people don't have labs. So, basically almost 75% of classrooms in Maryland do not have access to a science lab. So the key here is really just taking the average classroom and making sure that the curriculum that you're developing is something that can function in an average classroom. To be realistic, just so that you have a sense of the numbers, building a lab costs about $500,000 and will only serve on average about 10 sections of students. So that gives you a good sense of the fact that the black tabletop laboratory concept is not scalable from most schools and districts, just from a resource perspective. Next set of kind of questions here that are a bit interesting to look at. Are appropriate resources aligned to the NGSS available for science instruction in classrooms? And this is again from that educator's perspective, and really it's about 50-50 again, maybe a little closer, about 60% here, but nonetheless there's a great deal of folks, almost 40%, who don't have access to the aligned resources yet. Is technology available? And again, technology is available, but the resources for the instruction are not necessarily available. Again, 65%. So kind of the kind of picture that comes together here is that while we're in this transition, kind of looking at the timeline, there's been a lot of focus on technology. There's a big focus on the fact that college and career readiness requires the next generation science standards. that learning happens in 3 dimensions. There's practices and content and phenomena that come together as part of performance expectations. But in terms of professional development, it's emerging at 50% here access. The technology is there, but it's not necessarily integrated or providing an opportunity to deliver resources because folks are not identifying that resources are necessarily available. So there are gaps. That's the point here, is that there are still gaps. And when you look at the 5-phase implementation timeline that the Department of Education in Maryland has put together, basically we're going into, so that question survey was taken right here at the beginning part of the 2015-2016 school year. The 2016-2017 school year is aimed at implementing piloting assessments, but also having developed and evaluated resources and be implementing them, with the idea that through implementation, what you think is aligned, you may need to adjust, and you may need to actually move some things around, and what you've created may not actually be as well aligned as what you think. So really, you should be going into 2016-17 really thinking about implementing resources you've evaluated or those you've created and getting to trying to get as quickly as you can to a refinement level. And one of the reasons for that is that, and we can look at this a little bit later too, but the federal government has not relented on the fact that science needs to be assessed in the elementary, middle school, and high school levels. And so the assessments are going to change. They're going to be an ever-present part of this process, and they are going to align to the new standards. And as they do, they're very much, when you take a look at what these next-generation science assessments look like, they very much are requiring all 3 dimensions to be assessed, and they're actually assessing them. And when you think about the classroom instruction that leads up to students really being able to demonstrate proficiency of a performance expectation, you have to realize that one of the big shifts is classrooms focusing or sort of building off of the nature of science and engineering itself, because the next generation science standards give us a clear definition of what science is, what engineering is, and also what it's not. So science is defined as knowledge from experimentation, and that scientists ask questions and they form hypotheses, and they actually test those hypotheses by developing planned experiments that yield data, and that data is what they can use as evidence to form a claim and reasoning around their claim as to whether or not their hypothesis was an answer to that question. That's how knowledge is extended in the context of science, and so that gives us scientific knowledge. Engineers, under these standards, solve problems. And so engineers identify some problems and they solve them, and the way that they solve them is by developing technology, and that technology is not always something that's physical or electronic. The technology is simply something that solves a problem. So it might be a process or a software program, might be a doorstop or a hinge or something like a nut or bolt. Those are all examples of technology. Engineers use their knowledge of science to solve those problems. And so they look at available resources, they pick an approach, they diagram, they test, and then they build. If there's any kind of building, you obviously have to build a prototype, even if it's non-physical. And then you have to test it, and that testing yields data, and that data becomes the foundation. Well, you analyze it, becomes the foundation of a claim that you make about whether or not the prototype actually solves the problem. So math is in the center of all of this because it's the tool for quantifying, technically evaluating, analyzing, and communicating the results of these experiments, because scientists and engineers are both experimenting. They're just using a different process, and they have a different purpose for what they're engaging in. So they're complementary, and it actually forms this kind of cycle because technology allows scientists to answer questions they couldn't answer before. I mean, imagine the questions that we have about outer space that we just can't answer because engineers have not designed probes and technology that can get out there to actually sense and take the measurements that are required so that scientists can analyze them. But when that happens, scientists will be able to answer those questions and perhaps come up with new questions. And so this kind of forms a sort of synergy, and it's something that needs to be very clear to teachers, but also very clear to students. Students should understand whether they are in the role of scientist or engineer and understand the difference. It's really vital. In order for that to happen, it means moving away from a traditional model of science instruction. So we think about mastering these next generation science standards, it means changing the relationship between children and content. And the traditional model that most folks are struggling with is trying to leave behind this idea that teachers are the experts who demonstrate phenomenon, explain all about what this is, and model how to do something, or facts, explain, telling the facts. Because in this environment, the student's role is to absorb and remember and recall and be able to summarize and repeat what they've seen, what they've heard. And so in the traditional model, repeating demonstrations and summarizing phenomena is kind of the recall model of proficiency. And you'll see from the new assessments for next generation science standards that are being deployed at state levels in multiple states across the country at this point already, that these types of assessments are looking for skills and not recall. You have to be able to understand and remember and apply, but those are lower order thinking skills. They're really looking at creating, evaluating, and analyzing a context and something that's not the result of direct instruction, and that's really key. A traditional model functions entirely off of direct instruction, and I cringe a bit because a number of states have told, even within their timelines, and I believe you see this in the timeline I just showed you as well, that the idea of, you go through your existing curriculum and you try to add the practices in and then guide students in the practices. Well, you have to be careful with that word guide, because modeling a demonstration is guiding. I'll show you and then you show me. Okay, that's no different than recall. And so you have to be very careful with how you interpret that. And because these sort of things are not really guided, what they are is they're coached. The skills and the practices are really something that's coached. And so when you think about the role of the teacher in a next generation inquiry model, and this is true of kindergarten through grade 12, that the role of the teacher is not to get between the student and the content. The role of the teacher is to strengthen the connection between the student and the content by bringing them closer and closer together. And so that teacher's tuning the environment, they're helping the student understand how to engage appropriately, what the expectations are, and they're helping clearly communicate that, and they're creating a culture of critique in that classroom, academic critique, and peer-to-peer, and also student to teacher, and they're helping redirect and monitor what's going on in these student teams and as well as the classroom. And there's kind of, I'll show you an arc of one of the way that we approach this. So the teacher's role is absolutely vital. Without a teacher in this environment, it doesn't work. This is not something that can be automated. This is not something that even an adaptive computer program, whatever, can accomplish, at least not right now, maybe in 20 years or 30 years, but it's far too dynamic. What you see here is the students, having developed those practice skills, STEM science and engineering practices, which are skills, and they use those. It's a small toolkit, but it's a very powerful toolkit, and they use them in order to develop and use the content and to observe and understand and experience the phenomena. So those are the cross-cutting concepts and the disciplinary core ideas dimensions of these new standards. The way that a student demonstrates proficiency is to actually demonstrate the expectation. And so that means developing and using the content themselves. And by developing and using content, what that means is not discovering a new drug in the classroom. What that means is taking something that they have had some understanding of, and we could say some, like it's, and actually move with what limited understanding we have into an area where we have even less understanding, no understanding. So extending, developing and using means extending our understanding as students. And that requires using those skills to solve problems and answer questions. Okay, it doesn't have to be new to the entire world, but it's new to the student, something that they have not seen before. It's not been the result of direct instruction. They don't know how to solve that problem exactly. They don't know how to answer that question exactly. They're going to have to use their tools to use what they know to extend into an area where they are going to get the data. They're going to get something that they can use to actually form an evidence-based conclusion. And then furthermore, that they are going to demonstrate proficiency by using the behavior of systems and the content, not only to understand those disciplinary core ideas, but also to be able to describe how the disciplinary core ideas interact with each other. So this is a very different model, and one of the reasons why I say be very careful when you see, if you have a unit on light and energy, well, chances are it's not going to be much in there that's useful, because but you can fall into the trap of saying, well, light and energy is in the new standards, and it was in the old standards, and so, I can just use this and add some practices in. If your curriculum is designed for a next generation kind of model, then yes, that's probably going to work. And in fact, you don't have to add anything because those practices are probably already there. If, like most folks are running into this situation, if your curriculum is designed more for a traditional model of demonstrations and students kind of carrying out little culminating activities or trying to do an activity before actually showing a concept or something like that, has to go away. It doesn't fit. That's why the standards are designed to have three foundations. So this is the standard. If you're not familiar with it, you probably are been very familiar with these by this point, but it's a performance expectation. Okay, so this is a grade 5 example. A student, as a result of instruction, should be able to demonstrate their understanding by developing a model to describe the movement of matter among plants, animals, decomposers, and the environment. Well, how and where is this going to happen? Okay, where are they going to develop a model? Well, they're not going to do it in a molecular context, but they are going to do it in a context that emphasizes that matter, not food, is changed by plants into matter that is food. Okay, well, that's more helpful. So you can picture food chains, food webs. The foundation boxes come into play because these are the absolutely necessary skills that are going to be required to develop and use this particular content, the disciplinary core ideas, so that students are extending that knowledge, actually developing the model, and so on. And that's where they're going to be able to observe and demonstrate that they can connect the fact that this is a system. What we're talking about here, this model, is actually a system that we can describe in terms of its parts, but also how those parts interact. So you might think about that as like a food chain or a food web. There are parts like lettuce and grasshoppers and snakes, but at the same time you have producers and consumers. You also may have something like bacteria in here, and so you have an opportunity for matter to be recycled into the environment with life cycles, and and also the sun being in there in terms of where the source of the energy is coming from initially. So a student has to be able to look at an environment, a picture of an ecosystem, and this is what I mean by not the result of direct instruction. You cannot teach students every possible connection of every possible answer and every possible ecosystem because they're virtually infinite. So what needs to happen is a student has to be able to look at the properties of something and be able to apply the skills with some knowledge of the properties and the systems in order to generalize what they've learned, create, evaluate, and analyze the circumstance, and actually synthesize something new in that unfamiliar environment. And I'm going to show you some examples of that. The big shift here is in these practices, okay, and the fact that it's the student who has to have developed those skills. And at a high level, there are 8 of them. So when you look down this list, you probably can say, oh, students do all these things. Well, do they do them all together? Can they connect them? And on top of it, is it a skill that they have such that these blue or teal words are actually skills that they can demonstrate in a novel context. What I mean by that is, are they prepared to define a problem or ask a question in a scientific and engineering way? Not only use a model, but actually develop one. Not only carry out an investigation, but actually plan one. And that's the thing. This is number 3 is one of my favorites, because the investigations that you commonly see in high school and middle school and even in elementary school are kind of investigations that are handed to students. You know, put in, here's your lab, follow the procedure. Well, that means that the teacher has done the planning. The student has not developed the skill to plan that investigation. So they're not going to be able to demonstrate that practice. And so as a result of carrying out the planning and carrying out the investigation, students need to be able to obtain, evaluate, and communicate their information, analyze it, and interpret it. They have to use mathematical and computational thinking, because there are all kinds of orders of magnitude and things like that that get involved here. And constructing an explanation. They have to be able to argue from evidence and construct an explanation that uses that evidence to support their reasoning. That's part of actually determining whether you've designed a solution. So you can see that there's a relationship between all these practices. They interrelate. And then when you stick these practices, these skills in a student, and you put that student in a context, if they've really developed the skill, they're going to be able to pull these together and demonstrate the performance expectation. If they haven't, it's going to be really obvious. And it's kind of interesting, because several several states, not Maryland but others, folks have said, as these new assessments, students who are not able to perform on these assessments are not prepared for middle school. And it's going to be very obvious. And the reason is that it's based on these practices, okay, these skills. So at the second grade level, so here's a couple students at a second grade level. What you see involves all the practices. Okay, the practices come together in the scientific and engineering design processes. There are 2 different ones, and there are different flavors of them depending on who you talk to. But the bottom line is that the process is still important and valuable, because process is logic, and teaching children logic to be able to progress from an idea, or really in this case a problem or a question, to an evidence-based conclusion is invaluable, because that logic is what helps students to identify which practices they need to be using and how they're related. So practice and process are different but related in the case of science and engineering. Now, one way to kind of think about this is to think about it in the context of ELA. So in English language arts, we teach children to write. We teach them the writing practices like word choice, voice, tone, sentence structure. We also teach them the writing process, where the children apply those practices to create high-quality published works. So brainstorming, drafting, editing, revising, publishing. Okay, that's how you get from an idea to a high-quality published work. So both practices and processes have a role that are interrelated in writing. Practices and processes have a role that are interrelated in both science and engineering. And I want to point that out. They're relevant at all grade levels. What changes is the sophistication and complexity with which students answer and think about these, for instance, the types of plans and the kind of investigation students carry out are less sophisticated, and they involve less variables at the early grade levels than they do at the older grade levels, like grade 4, 5, and 6, or even into high school. These are some 5th graders. They're engaged in engineering. And when you think about how the class unfolds, and if you'd like to take a look at how this is set up from a teacher's perspective, you can check out at noadam.com /curriculum, or you can just go to the page and click curriculum at the top. You'll scroll down, you'll see for each grade level there's curriculum samples. So when you look at that, what's happening is that these students have gone through a kind of experience in this next generation inquiry environment where They've had some nonfiction reading that takes the concepts and anchors them in real-life context, and it scaffolds. And then they've engaged in Socratic dialogue in their classroom. So the teacher has been skillfully asking questions to cause the students to have to use their higher order thinking skills, to have to create, evaluate, and analyze in their response to those questions. And then that teacher in that Socratic dialogue has not been validating those responses, but actually that they have been looping other students into the conversation and asking their thoughts and what evidence they would have to support their opinion about what claim or concepts a student has made, and so on, sort of creating those triads. The purpose in mentioning this is that things like Socratic dialogue replace traditional lecture. Okay, it's not about explaining and saying you're right, you're wrong. That's right, that's wrong. What it's about is it's about teasing out the children's ideas, and when you have children that are spot on and children that aren't spot on, helping them help each other by asking those higher order questions that bring the right information into focus and clarify misunderstandings. And then what you see happening here is that students, the classes come to a problem or a question, which now they've broken into their small groups, so you have that small group learning happening, and it's project-based, hands-on, and these students are trying to take apart and solve that problem. Okay, as engineers, they have to take their practices, those skills, and they have to take their knowledge of the engineering design process and actually try to solve that problem. Go from their idea to a prototype, to a test of that prototype, to some data, and then use the data to support whether or not the approach they took solves the problem, or does it need to be refined. That's what they're doing here. Nobody has shown them how to solve them. But the thing is that it's well designed so that it's within reach. Okay, so it's not too far afield that, you know, if they don't have some extra specialized knowledge, they have no chance of success. It's within reach, but it's going to take some work and effort, and they're going to have to prove their concept. So that's key. That's what makes this student-centered, that's what makes this minds-on, and that's what makes these next-generation science standards really something that is fully integrated, because the standards were designed with ELA and Math Common Core in mind. So one of the shifts here is to really think about the science classroom as a classroom where students are developing nonfiction text. That's what's going on here. These students are planning in blank composition notebooks beginning in the 4th grade level, and they are using a process, scientific process or engineering design process. Now that doesn't mean that science and engineering are linear. I don't want you to mistake what I'm saying. It's not prescriptive. What it is it's logical. So students are using logic to help guide their application of their skills to trying to solve the problem using their own thoughts and ideas and bringing those to life. So that accomplishes in many ways through the nonfiction reading and the writing ELA technical subject standards, writing standards, and communication standards under Common Core. For math, they are quantifying observations, analyzing them using mathematical operations, and they are absolutely applying all of the Common Core math practices and you know, other things too, like graphing and so on. So this next generation inquiry environment is a really rich context for applied ELA and math. What's only science really is the experimenting, the prototyping, and the planning. However, the planning is still a process writing, so it's kind of hard to plan without you know, involving some ELA and also math, because the plan needs to be specific. So when we think about Bloom's taxonomy, traditionally we think about a 6-layer pyramid: remembering, understanding, applying, analyzing, evaluating, creating, being in that order, lowest to highest order of thinking. With the new standards, you really need to kind of reorganize some of that in terms of, you know, we're not isolating one aspect of higher order thinking anymore with these standards. What we're doing is we're bringing creating, evaluating, and analyzing into contact with each other so that students are engaging in them simultaneously. So if there's a problem, you have to try to create, you have to evaluate that problem, you have to analyze the problem, you have to try and create a potential solution to it, actually create a plan of how that is made, whatever it is, whether it's physical or virtual, and then you have to actually carry out the plan, evaluate the results analyze the results, evaluate them, and use that to create an explanation as to whether or not the approach that you took solved the problem. And the thing here is that grading is not about having a hypothesis that's supported or not supported, kind of true or false, or having a prototype that solves the problem or not. Grading is all around the student's ability to demonstrate their skills and knowledge in context, and to be able to form relationships between the content by understanding how that content interacts. That's what the phenomena is. So without creating, evaluating, and analyzing being the focus of the classroom, students are going to have a real struggle progressing in future years, which is why a lot of these state education leaders have stood out and said, hey, look, if a student can't perform well on this assessment at the elementary level, they're not prepared for middle school level. Bottom line is that if students don't perform well, students aren't really well equipped to think at a higher level, and that should be really alarming, because that's what makes students employable. That's what makes them attractive candidates to employers, but also to colleges and career prospects as well. So it's all interrelated. What I wanted to point out is one of the first in the nation NGSS aligned assessments that's right around the corner from you in DC. What's interesting is DC has kind of, and I'll say this kind of facetiously, opened shop on their assessments and have become kind of an assessment company of their own, in a sense, because what they've done is they got an early start on piloting and actually field testing NGSS aligned state level assessments, and so they've been on this for a couple years now. This year, so the spring 2016 was the first operational assessment, and Illinois jumped on board and basically began borrowing their items. They created an item exchange agreement, and so those assessments exist, and other states are intending to do the same as well. So what I wanted to point out to you here is just that it's an assessment at the grade 5, grade 8, and also the high school bio level, and the assessments do not while they take place in grade 5 and grade 8 and so on, they are not grade level specific. What that means is that they're not only testing grade 5 standards, what they're testing is all of the standards in grade 5 and prior. And I bring this up because one of the big misconceptions in the way people are creating their curriculum is they see grade level standard and they think that's the grade level that it's taught in only. And that's the misconception, only. You see, the grade level standard has to exist in the grade for mastery as a focus, for mastery. But what needs to be happening is, and if you look at the peak alignment criteria, so PEEC, that was put together by Achieve, it talks about pooling standards, and actually the EQUIP for science rubric talks about this as well. You're not teaching these performance expectations in isolation. You're not isolating the dimensions, you're not isolating elements, you're not trying to create a list and check them off as you go, one at a time. You're also not handling them one at a time in isolation. So you're pooling them together. So what that means is there are going to be multiple standards that are related to things like ecosystems, because ecosystems also relate to things like changes in matter and energy, and also food chains and food webs, and phase changes and water cycle, and actually how the Earth's surface changes, so erosion and weathering, because ecosystems exist in specific places under specific conditions, and if you change any of those, it impacts the system. Okay, life cycles even are aspects of this. So the reason I'm trying to bring this together for you is that when you think of a grade level, that grade level is reinforcing standards from the prior grade level. It's focused on mastering standards from the grade level, and it's also supposed to be introducing standards from future grade levels. That's what the role of curriculum is. It's to get students nurtured September through June, but also from one grade level to the next. That's why we call it vertical alignment as well as horizontal alignment. it's really important because when you look at these assessments, it's important from a student's perspective because they're not always at the right place at the right time developmentally. Another reason is that students are absent, they're latecomers. If you only address a 5th grade standard in 5th grade, then what happens to the student who comes in 6th grade and didn't have exposure to that standard previously? It's a gap. And when you think about testing happening at 5th grade, if you only cover the 3rd grade standards in 3rd grade and 4th grade standards in 4th grade, when that student comes in 5th grade and they're tested, even if they're the best student, 100% mastery, they are going to have gaps from 3rd and 4th grade, and they're going to show up on that test. And they're going to show up in their understanding as well. So it's really important to understand that that these tests are not grade specific, that they're actually pooling the standards, and that your curriculum should do that, because the job of curriculum is to get students to proficiency. The role of the standards is just to help you understand the context and the expectations of the students who are deemed to be proficient. So in DC, this is what their assessments look like. Okay, and these are the examples of items that they have been sharing with other states and other states have been adopting as their own. They fall into multiple choice, open response, and what's called a technology enhanced item, because these are, at this point in time, are computer-based assessments. So the common piece here is that they are based on scenarios, and they generate themes with sort of fictional students, and the scenario really mirrors what a student hopefully should be able to relate to from their class, because the scenarios are often involving students, fictional students, engaged in sort of a fictional experiment, forming fictional procedures and carrying out fictional scientific diagrams, gathering fictional data, and then coming to fictional conclusions. Now, they're realistic fiction, but what the real student who's being assessed is going to be asked to do, and you can read it right here verbatim, which of these fictional students' claim is correct? Explain why the claim is correct and use evidence to support that choice by studying the tables and the claims that these Trevor and Kayla, the fictional students, have made. So you can see here that those skills that we talked about earlier are skills students are going to need to do to be able to engage in, use their higher order thinking. You can't teach this scenario because you don't know what it is. It changes every year. The students change, and there's an infinite number of them. So your student needs to be able to, as a result of their instruction, be able to analyze and evaluate this situation, create their own claim about the fictional student's claim, and then use data from the scenario to support their claim. That's how they're going to demonstrate proficiency. So that's why I say, back to the old curriculum, the old traditional model, it doesn't work, it's broken. And that's what the shift is all about, getting away from the old broken model to a next generation inquiry model, and developing that skill set in students so they can step into an unfamiliar context like Trevor and Kayla's fictional world of hydroponics versus soil grown beans, and be able to evaluate the conclusions and come up with an evidence-based claim that's well-reasoned. Now, this is a constructive response. This also applies to what's called technology-enhanced items, which are like drag and drops, which you see on the left, as well as multiple choice. And multiple choice is getting more sophisticated. It's not a question of what is the right answer, as in single right answer, but in fact, which of these are the right answers. So plural, 3 out of 6, 3 out of 5. So that old idea of being able to just eliminate 1 or 2 and get a 50-50 possibility is much more difficult now. Students, even in this drag and drop kind of model, what they're going to have to do is be able to look at the organism and then think about its characteristics. Does it fall into producer, consumer, or so on? Is it a herbivore, an omnivore? Is it a carnivore? Drop it into the food web, and then there's actually a followed-up open response. Explain this is, and these are, you're going to see these being tweaked a little bit more because the wording is not quite right in their assessments even still. That's why this, is a work in process. But what the students asked to explain is the shortest path for energy to get from a producer to a consumer, in this case the lettuce to the fox. the multiple choice that I was explaining about earlier, the student is given a scenario. And notice, by the way, that the fictional students that were here earlier, Trevor and Kayla, they are following through in the other items. And these items are all related: plant growth and development, and the requirements of plants to live as living organisms, food chains and food webs, and then over here we have matter cycling through ecosystems, energy transfer, and transfer of matter. So this is a different ball of wax from the old days. But at the same time, it's something that students are very capable of doing. But the problem lies in whether or not students have been given an opportunity on an everyday basis to engage in actually attempting to engaging in attempts to demonstrate the practices and engage in those practices and really demonstrate the performance expectations. Because you can see here that student has to select 3 out of the 6 as the correct answer in response to which of the following statements best describes the movement of matter in the pond food chain. But then they have to give a constructed response, so it's an open response to model. So using the model of the pond food chain to describe the relationship between organisms in the pond food chain and the exchange of matter back into the environment. The key piece here is life cycles, because you really have a food web and other food chains going on here. If a minnow dies, the bacteria will recycle that matter back into the environment by decomposing it. All right, so that's kind of the food chain situation. You have the life cycles and the minnow dying, and that matter being returned to the environment so the algae can uptake it and go ahead and just send that right back through the food chain again. And there's other things too. Students can have different depths of thinking as well, because there is grass shown over here and kind of other ways of the matter being distributed back into the environment. But the key being that the bacteria gets involved and we actually have the connection to a life cycle and a separate food chain. And so we have a food web at play. So that's key. A student has to be able to reason this. And then you see again 5 and 6 here, the same characters come up, another multiple choice, another open response. So don't expect identify which of the following is a sedimentary rock. Those questions are gone. They're gone forever. It's now about really considering the interaction and analyzing the circumstance. And even if it's a multiple choice, engaging in that in order to be able to select the answer or the multiple correct answers. So why is it that the standards and the assessments and all these sort of things require this kind of shift in the classroom? And it goes all the way back to the National Research Council, and really there was a report that they had done prior to the development of the standards. It was really looking at effective K-12 STEM education. You can download the report for free right from the National Academies Press. But nonetheless, what it was highlighting is a shift from what you see on the left to what you see on the right, and I described what's on the right earlier. Right, the students haven't seen a circumstance before. They just have some skills, they have some understanding, and now they're going to extend that. What you see on the left is that old traditional model of I'll pre-teach, I'll model, the kids are going to look intently at what I'm doing and then go back and do it for themselves. Something like that is, you have, in this case, a teacher doing a demonstration. If a student goes back and then does the same thing, all that is a students repeating a demonstration for themselves. And that's kind of an old KIT model that you see, read all about it, learn all about it, and then do the culminating activity, or fill out the worksheet by using the rocks and doing the scratch tests from the KIT. Doesn't fly anymore, because this is the National Research Council's definition of effective science instruction. Effective science instruction capitalizes on students' early interest and experiences. That means it starts early in kindergarten, pre-K, follows a child all the way along. It identifies and builds on what they know, so it's intentionally nurturing. And that's true within the year from September through June, but also from one year to the next. And this is really the job, when you think about as districts get larger, so if your Baltimore public schools, you are at a scale where administration has to make this happen. If it doesn't, then what happens is as students move between those buildings, or between those classrooms, they're getting entirely different experiences. It's not nurturing and understanding, it's actually fragmenting it. In small districts, sometimes you can get away with, not really thinking systemically in terms of identifying and building on students know, because people are in close contact and there's not that amount of variation. And then small districts, and again, it really depends on the socioeconomics of the district. You may not have the level of transience in your community that you have it elsewhere. So things tend to be more stable, is what I'm saying. So where things are less stable, having a well-articulated scope and sequence, for instance, having well-articulated scaffolding vocabulary, having units that are intentionally scaffolding, having teacher support resources that are making sure that the teacher can have a well-informed Socratic dialogue with those students is vital. Okay, so those things help every district, but as districts get larger, it becomes really not an option, because without it, these poor children end up with a really fragmented understanding and it becomes disorienting. So identifying and building on what the children know intentionally is that nurturing process. Providing them with the experiences to engage in the practices means that the classroom learning, the pedagogy, is facilitating students in the role of scientist and engineer, putting them on the front lines, putting their thinking on the front lines, and really challenging them to engage in those practices. It's kind of like putting a child on a bike. And you can't learn to ride a bike from a book. You can get some basic ideas and some pointers, and at some point you have to get on the bike and you got to pedal. And you're going to kind of wobble, you're going to fall a few times, and that's where the teacher as coach comes in. Helps the child get back up, get back on, keep going, and help kind of redirect and correct a little bit and keep on going. And before you know it, they're riding the bike. But you can't ride a bike by reading a book. And so because it's a skill. And the same is true of the practices of science and engineering. You can't learn them by being told about them. You have to learn them by engaging them, by attempting them, and by learning really by experiencing. And that's why that word experience and practice is so vital in this statement of effective STEM instruction. Sustaining student interest is really a key factor, right? Because when you put students thinking, you empower them, you put their thinking at the forefront, then you're empowering them to actually use their ideas, and this is, I guess, the key piece of the empowerment. If students can use their ideas, bring their ideas to life, it doesn't mean they can just do anything randomly, but what it means is that you're challenging them to use their thinking to solve a problem or answer a question and do it in a novel way, then that's really engaging, because it's not repeating something somebody else has done, but it's actually creating something and doing something I want to do for myself. And it's a tangible, if it's hands-on, it's a tangible piece of success as well, and learning opportunity. So that's very engaging and sustains students' interest. And the scope and sequence is really a key part of that too, because this old 3 and 4 unit a year model is like, it's like a million things you can do around earth science, for weeks and weeks. That doesn't sustain students' interest. It actually is the opposite. What you want to do is you want to slice really closely and in a focused way and your units so that you're close to the standards, you're pooling the standards, and by doing that you're creating a context, and then one unit to the next the contexts evolve in a sense. You get a year-long narrative, but at the same time you get within that narrative almost like weekly chapters in a sense. The way that lessons, in the case that the way we approach it anyhow, and we found to be really effective with thousands and thousands of kids across the country, is to engage that key pivot from the peak alignment criteria of pooling the different disciplines, so STEM as well as ELA and math. And you start with nonfiction reading. And I'm not talking about reading entire chapters for days and days and days. I'm talking about 20 minutes of reading. And then Socratic dialogue, 20 minutes of Socratic dialogue. And then transitioning to student investigations, where there's a problem or question, you break into your teams, and then students may spend an hour planning their investigation. And the thing is, this is taking place over the course of different days, right? So don't picture this as to shut down my whole school and just do science. But they plan their investigations. So the problem or the question is the purpose. The plan is how you try to achieve a solution or really a resolution to that problem or question. That's the purpose of the plan. Carrying out the investigation is how we get our data. That's the purpose of engaging hands-on in a project, right? In an experiment. Because the thing is really not a project, it's an experiment. And then that data allows us to form evidence-based conclusions, which are, evidence reasoning, and that can be shared as part of a debrief and transition to the next lesson or unit. So that's the model we use. So if you do look at one of those, see that coming to life, and actually you'll be able to get basically a month's worth of any grade level that's up there from a teacher's perspective, so you can see what that looks like, and then from a student's perspective, what the reading looks like as well. And there's other pieces, the processes that I mentioned earlier, they're similar but different. The pieces come in different order, and those are specific to engineering and science, so that's kind of a key piece in that environment. And then bringing science and engineering together is really important. And we're coming up on the hour mark, so I'm just going to let you know I'm going to take maybe another 10 minutes. I am going to grab any questions if you have them, and feel free to reach out to Mary Ellen. My name's Francis again if you have any questions that don't get answered or you leave early. So engineering and science come together. I'm going to give a grade 7 example, and this is one that is from our curriculum. So students are learning about science, the science of, and you can see how standards are pooled here. Phase changes, you have the impact of temperature, thermal energy on phase change with the water cycle, but then we have the connection to earth materials and earth through how water affects earth, and actually how rain and runoff actually restore groundwater aquifers. And so the basic science of earth materials and how they have different levels of permeability. Okay, so permeability being how water can pass through different earth materials differently. And so as scientists, students engage in answering the question of which earth materials are most permeable to groundwater, and they form their own, using the scientific process, they form their own investigation. They diagram it, they actually carry it out using the materials that we've made available, and they gather their own data and form a conclusion based on analyzing that data and evaluating their hypothesis. Okay? In the next lesson, they learn about pollution, and they learn what pollutants are, and they also learn about the connection between surface pollution and groundwater. So now you can picture that water cycle going on, and this is what's really cool about the next generation science standards, is you can do these sort of things, and they really help develop the students' skills and understanding across all 3 dimensions, and their ability to perform the expectations. So they learn about pollution, but then thinking about what they learned about previously in this context with science and groundwater and aquifers, and so they're able to connect pollution into that environment and understand the idea of non-point source pollution, where over time pollutants far away can travel to wells nearby. And the idea of groundwater aquifers being kind of tainted. And they can take on the role of engineer then to consider the challenge of removing pollutants from groundwater. And so here you can see it's a different process. Looks similar from afar, but actually it's a different process, using the same practices though, and they're going to engage the problem of a fictional town that needs low-cost water filtration devices, and so they're going to engage in looking at what they know in research, those facts, surveying the available materials, and then considering a solution, diagramming it, testing it, gathering the data, and then using that data to decide whether they need to refine or replicate their prototype. Okay, and then what's great about this is then you think about that debrief, students can say, hey, here's how we reached it, and then in this case we are assigning cost to items, so they can say, well, we had a similar result, but ours was more efficient from a cost perspective. In other cases, they could say, well, maybe that's more efficient from a cost perspective, but it's not probably very practical to scale, or so on and so forth. So you can get really great scientific argumentation happening in these debriefs, even at the earliest levels. Remember what I said is that it's all relevant at all, kindergarten through grade 12, but what happens at those K1, 2, and even 3rd grade levels is Students are going to see aspects of these things. It's going to be less sophisticated, but other aspects they may have to follow, so it's going to be a little bit facilitated. And if you look at one of the early lessons up there, you'll kind of see how that works too. Anything that is being assessed at a state level or anything that we're teaching really needs to be something that's able to be assessed in the classroom. So think about the classroom assessments that you're developing as being assessments that should mirror what we were discussing earlier at the state level type assessments, and really thinking about those scenarios and then teasing out aspects of the different dimensions and challenging the student's thinking to be able to quantify whether or not the student has mastered related to the performance expectation, whether they're really performing that expectation. This is an example from one of our units too. I believe this is a 7th grade example. If you want to download that and take a look at this literal one, you can. Okay, so I mentioned ELA and math connections with Common Core. Here's a couple examples. Following precisely a multi-step procedure, that's ELA, not science. Following is not science. Creating the multi-step procedure is science. Expressing information visually, distinguishing between facts and speculation, and reasoning that. These are just a few examples of many, and these are from middle school. Another piece to take a look at is those Common Core math practices. Here they are. So imagine this is Common Core math, and it relates directly to the science, making sense of problems, persevering in solving them, reasoning abstractly, constructing a viable argument. I talked about that culture of critique as being that next generation inquiry environment. Critiquing the reasoning of others is a Common Core math practice. Modeling with math, using tools appropriately, attending to precision, using structure and reasoning with expressing regularity and repeated reasoning, which is basically the idea of trials and recursive steps and procedures and things like this. So nonetheless, all of this is applied in this next generation inquiry context. So really key. The challenge around resources right now, and I'm proud to be a part of No Adam because we really have we got here. I really feel like we got here first. We did because we were developing alongside all of the releases of the next generation science standards, and actually we're able to produce data under existing tests that were not aligned to just show the benefits really of a next generation inquiry environment on even the student's understanding of the existing frameworks. So with the publishing of the next generation science standards in 2013 and then the subsequent adoptions, we've been aligned for some time. So we're one of the few, but the challenge really is that if there's a sea of resources that claim to be aligned or just aren't aligned, some people have made on their own, others that are commercially available, and they kind of fall into 4 categories, and I'll just really quickly cover these so you can get a sense of what I mean. So there's awareness level resources. They're kind of the lowest level. Get them from museums. They get some donations from folks. They make little things to help students understand, what's an engineer or whatever. As a result of that, a student is not going to necessarily be equipped with all the skills necessary to engage in engineering across the strands. Because remember, again, that it's the applications of science and engineering and technology. So thinking about awareness as making students aware of kind of the basics. That's what an engineer is. Now, companies often create these two to kind of say, here's how we use science at our company. Knowledge readiness resources are things like textbooks, the pretty pictures that go along with the explanation of the word. That's how textbooks are typically created, a paragraph to explain a word, and they try to scaffold those. That's teaching students all about what scientists have discovered, or engineers have technology they've designed, but that's backward looking. If there's anything I hope you take away from what we've talked about this hour, it's that the next generation science standards are very forward looking. So it doesn't mean that the past is irrelevant and that knowledge is irrelevant, it's just insufficient. And so students need that thinking and those skills. Performance-ready resources are like kits. It's basically task readiness. So if a student needs to carry out the task of finding the hardness of a rock, they have had an experience where they have carried out that task. We learn all about rocks and minerals, and then the culminating activity with the kit is that we give the students some rocks and they fill out the sheet. the hardness of the different rocks. Okay, that's performance readiness. Still insufficient. Mastery readiness is about what we described earlier, having the skills to engage in a context and then extract and develop the necessary information in order to form an evidence-based argument in favor or against something. So an example of that could be, the scenario of, in an everyday life sense, the carpenter or the contractor who's building a kitchen, a commercial kitchen, and needs to decide what is the most durable and cost-effective material to use as a countertop. Is it something that's plastic? Is it something that's glass? Is it something that's stainless steel or granite or marble or wood? And given the data, so imagine a student presented with that scenario. Maybe the contractor believes that this might be marble is the best countertop. Well, the student has to look at that, maybe look at a data table and be able to look at the scenario and take it apart and actually make an evidence-based recommendation as to whether or not that contractor's made the right decision, or perhaps there's an alternate decision that would be a better fit. And by the way, it's not just that plastic is the better fit or stainless steel is the better fit. Here's why, with specific concrete evidence that they've gleaned or analyzed from the table. So that's mastery readiness, and that's really what we aim for. And just kind of in closing, we had mentioned art and the connection to the arts. So a lot of folks are talking about the idea of STEAM these days: science, technology, engineering, art, and math. And unfortunately, they get kind of bogged down in this idea that art is about making things pretty. And they kind of enter into this misconception that the role of artists in STEM, in science, technology, engineering, and math, is to make things that engineers engineer pretty. And artists, that's not their job. That's not even what an artist does. An artist engineers communication. They send a message through a medium. And that medium may be sculpture, it may be oil on canvas, it may be dance or music, but that's what an artist does. So unfortunately, artists are kind of fundamentally misunderstood. The reason I bring up Pablo Picasso and Guernica here is just because they're ubiquitous. It's hard for folks to have not heard and seen of these two. The reason that artists like Pablo Picasso end up in exile is because when they communicate things, and depending on where they live, if they don't have freedom of expression, sometimes they communicate messages that are unpopular with certain groups. And so Pablo Picasso created Guernica, living in exile, because he was commissioned to do so for an international art exposition. And he created this piece called Guernica, and it was about the atrocities at Guernica, this particular village in Spain. And what he did was he sent a message to the world and to the fascists about those atrocities through this painting. So this painting is not particularly pretty or beautiful. It's actually kind of downbeat and monochromatic, and it's in sort of Pablo Picasso's particular aesthetic style, but it would be out of place in a lot of environments. It's not sort of the interior decorator's concept of pretty. So the point I want to make with this is that the fascists came back to him after seeing this, and they said, "What did you do?" And he said, "I didn't do it, but you did." And so you can tell in that statement the level of deliberate execution and skill. And the connection here between art and science and technology and engineering and so on is these critical thinking skills, the communication skills. And so by training students with science and engineering practices, what we're actually doing with those higher order thinking skills, we're actually training them to be better producers and consumers of art, and specifically communication. And that's huge. That's absolutely huge. And on the flip side, when you think about artists, that culture of critique is very much the environment that make artists. Sometimes that's informal, sometimes it's formal. So you go to an art school, what's happening is the professors are looking over the shoulders of the students and asking questions about why they've chosen and what they're trying to communicate, and the particular color, or particular medium, or so on and so forth. That's what that's about. It's not about it's pretty, it's not pretty. So I just want to make that mention because it's something that has been gaining steam, and no pun intended, that it bears, thinking about your art classes. Your art classes are an opportunity to leverage the science and engineering practices, those higher order thinking skills, if you're focusing on helping children learn how to communicate their ideas precisely and targeted and engaging those the skills that we're teaching elsewhere. So I mentioned earlier, curriculum is sort of the foundation. The materials serve the curriculum. The professional development's job is to help educators take their existing skill sets and transition out of a traditional model, if that's where they've been, or a different inquiry model into a next generation kind of inquiry model, understand the resources they have, and so on. So when all those pieces fit together hand in glove, and that's what I mentioned earlier about not having systemic gaps, and not having sort of that fractured experience and intentionally nurturing, that's where the real magic happens for STEM learning. And so, we're an option for that. There certainly are others that, if they don't exist now, will exist soon. But feel free. What you can take a look at is the first unit of each of the grade levels online. See the students component and the kind of materials that are involved, and then we have all the others. They just are available for purchase, as well as the materials and things like that. We have to keep the lights on somehow. But I'm going to take a look here at the questions. I'll show you the quick data. So I'll give you 3 examples from Massachusetts, so you have apples to apples. Massachusetts state average is 50% for advanced and proficient. This particular school, over the course of 2.5 years, nearly doubled, basically hit almost 90%, going from the mid-30s in advanced proficient scoring students. The shocks that you see here are the result of changes in teachers and administrators. So teachers and administrators absolutely matter. That's what I meant earlier about stability being a key factor and an issue as things scale. What's nice, though, is that because systems were in place, you can see that despite those shocks, the students didn't fall all the way back to the original levels, but what they have done is been able to pick up and continue on. And these were some larger shocks, but you see a positive trend. Okay, this particular school is very inner city. It's 72% low income, 75% high needs, 65% free lunch, and 35% ELL students. If you look at a middle school of similar, actually even worse, more challenging, I didn't say worse, I mean, it's not worse, it's just more challenging environment. Here's a middle school, was bottom in the state, and 4% proficient, 54% failing and warning. And you can see over 2 years, system went in place, so got up and running with no Adam and so on and so forth, and they were able to add 24 points over the course of those 2 years. And look at what happened to the warning failing students, how they went from 54% to 27%. Now the key to understand here is that they're now performing at the level of their peers in the other 26 largest cities in Massachusetts when you average them. So it's really quite a feat, and we're really hopeful to see that continue. And looking at the demographics, it's even more severe, as I was mentioning. 95% low income, 87% free lunch, 97% high needs, 64% where their first language isn't English. And it's an opposite, if you're in more suburban or even rural environments where there's stability and you don't have quite the level of high needs. Like this case, there's only 20% high needs and 7% low income. You can see you get immediate gains, and then you're able to sustain those gains. And what the game here to get from 80 to 100% is really, you have to push every last button in getting the students to really engage their thinking. So there's more refinement possibilities, but you can see still major gains to the point where these folks are basically double the state average, and actually the highest school district in the state is ours as well. They're 90%, you can see that. It's really quite something. So I'll take any questions. There's another webinar in the series. You're welcome to jump on that if you'd like. It's available on demand, noadam.com/strategically, which really talks about the implementation of the NGSS sort of operationally as a district, as a school, how you want to make that happen. Feel free to reach out to Mary Ellen DeLacy. She's a curriculum specialist here if you have any questions around that or anything you've downloaded. Her email address is mdelacy@noadam.com. Her telephone number is 617-475-3475. And here's a list of different ways you can stay connected with us. All this stuff's free, and available online. You can subscribe to our blog, follow us on Facebook, follow us on Twitter. Check out under the free resources, under the resources section on our site, we have all kinds of ebooks, on-demand webinars, upcoming live webinars, and so you're welcome to dig through there. There's a really great one on Socratic dialogue. I would mention a whole hour dedicated to really the step-by-step of how to hold a Socratic dialogue that I'd recommend. And you can check out case studies under noadam.com/results. And as I mentioned earlier, the sample curriculum from a teacher's perspective, about a month's worth, you can check that out, and also the students' reading material, noadam.com/curriculum. So I'm looking at the questions. I'm going to have time. I'll take 2 questions here. One question I think we've already covered. It's, do we need textbooks? And the answer to that is it really depends on how you view a textbook. The basic answer is no. Textbooks are not the foundation of learning in a next generation inquiry environment. They're not a majority of the learning. What they are is a springboard. They really are, they're a basic foundation. And the thing is that having a textbook that has a paragraph that explains a word is not engaging. It's not, you can have all the pretty pictures and things you can click. It could be an electronic textbook. It can be, the wiki textbook of interactive and, all kinds of modular greatness. But the bottom line is that the way we approach nonfiction reading is to take a concept and anchor it in reality. So we'll talk about something like groundwater by talking about an actual sinkhole, like the Corn Bayou sinkhole. And now the students have a real life place and context for groundwater and its effects. And then what we do is we scaffold that up, sort of basically like each page it's as if each page in the reading is a kind of article where students are learning one context that connects to the next and so on, using the concepts and vocabulary in context. And the thing is that as a result of reading all of that, that doesn't mean, they haven't mastered anything. What they've done is they've gotten a real life context that they can then create concept to concept, concept to self, and concept to world connections to. And that acts as a springboard into Socratic dialogue, where that gets further reinforced verbally, and again, skillfully as the teacher's asking these higher order questions and looping students in to that discussion and bringing it to life through discussion, and then a real full release responsibility happening, not without accountability, because you need checkpoints as well, really, regular and frequent checkpoints. But that full release responsibility for students to do the real learning, which is engaging in the practices, engaging in the context, and developing and using the content. So think about the Socratic dialogue as accessing what was that basic foundation, and then developing and using it by being scientists and engineers, carrying out the investigations, and then coming back together and debriefing again in that kind of Socratic environment. So I hope that's helpful. And the last question here has to do with the ELL students and special ed students. So thinking about ELL and special ed, so the real key here is students are verbal first. And so when it comes to the example I just gave, those students are not going to have to master from a text. And in fact, you can read aloud. And by reading aloud, you're creating the opportunity to ask questions. So there's a whole bunch of really kind of key opportunities to take learning off the page and make it something that's hands-on, project-based, and actually something that students do not have a word in their native language to talk about or describe, so it becomes a tool for language acquisition. And we have a lot of great data around the effectiveness of this in those kind of environments. And it's been commented by state observers on more than one occasion on how amazing it is, the level of engagement of ELL students in science in this context. When it comes to special ed, it's it's a different flavor of the same story, because basically all you're doing is not removing the challenge, you're not removing the content, you're not removing the opportunity to learn the standards and master them, but what you're doing is just removing the barrier according to that student's IEP. So instead of, if it's something to do with a fine motor skill, language-based learning disability, whatever, student doesn't have to read something on paper. They can use a Kurzweil reader, they can use, so it's auditory, they can use either an Adobe or a Kindle kind of read aloud plugin, all achieving the same goal, but just removing the barrier of the actual physical sort of characters of text on a page. When it comes to things like creating a lab plan in a lab notebook, whether it's electronic or not, that shouldn't be a barrier. It doesn't mean that you throw out planning. It doesn't mean you throw out lab notebooks. What it means is the student may be using a scribe, they may be using a voice-to-text program, they may be having something like that going on. They are still responsible for articulating their thinking. And then the last kind of piece that you may find in that environment when it comes to special ed is students who are, for one reason or another, below grade point level or grade point entry level. And around that, what's really great is that you have the opportunity to throttle back to a prior year and work that way if the student is allowed to be operating below grade level. Or on the flip side, if they're functioning sort of below grade point level but at grade level as required, what you can do there is, like in our case, we have below grade level entry points where we give support for differentiating instruction and gathering primary evidence, basically for portfolio assessments. And that's the key, is to understand that students still need to participate and be engaged in all of the practices and processes and the disciplinary core ideas and attempting those performance expectations. But it just means that by being below grade point level, it's kind of like they're starting at a lower point, so they're not really ending in line with their peers either. You're trying to get them there, but there's this bit of a gap. And so what you can do in terms of portfolio assessments is segmenting and really isolating aspects of the standard, which you shouldn't be doing anywhere else, but in this context is appropriate. And you gather that evidence, and then you can use that as proof of the student's learning towards specific educational goals that have been defined for them. So that's the way that works. I really appreciate your time and attention, and I hope that you found this helpful. If you have any questions, like I said, feel free to reach out. I'd be happy to answer any of those myself, and if you have any questions around other resources or adoptions that you're engaged in at this time, feel free to reach out about that as well. I wish you luck on engaging in the next generation of Maryland's science standards. My name is Francis Fitchin. Have a great day.